Let's try to understand the different types of problems that we might get based on which we can solve different equations related to partial fractions. So, and that depends upon how the polynomial is structured in the given problem. And let's talk about that. And in this episode, we are just going to talk about proper fractions and not the improper fractions. Improper fractions, we are going to consider it separately. So just based on the proper fractions and just depending upon the denominator, we can segregate them into three high level of types. Okay, the first one is called as non-repeating linear factors. Like you check the denominator and you might see that the denominator kind of fits into this model where it has got non-repeating linear factors, or you might have a denominator which might have a repeating linear factors, and last but not the least, you might have a denominator in the polynomial which is quadratic in nature and which cannot be factorized any further. And like I said, improper fractions will be discussed separately. So just in the context of proper fractions, for solving partial fractions, we have got these three types of different expressions. Based on that, we can solve this problem. Each one is a different unique method to solve, which we will see in the next episode. But in this episode, let's get introduced and get an idea of what each expression might look like when we talk about these three types. Okay, let's jump into the first one. The first one is something called as type 1 for proper partial fractions. And I'm going to just emphasize proper because we're not going to discuss the improper. And the type 1 is non-repeating linear factors. And what does it mean? We'll come to that in a minute. Okay. So let's say we have a given expression, rational expression over here. Okay. And let's focus on the denominator over here. So what we say is, like we saw in the previous episode, after checking for proper and improper, the important step is to see whether the denominator in specific can be factorized into simpler versions. Is it possible? Let's check that. In this case, yes, it's possible. And I've taken the same kind of expressions that we saw in the previous video. If you don't recall, just check out my previous episode. It's the same examples where I mentioned the steps, factorize wherever possible, and then we can see what happens when we cannot factorize. The same examples I've taken. So check out that video in case you need a quick refresher. So what do we see here is in the type 1, we see non-repeating linear factors. So what does it mean? We take the given expression. Let's say if this was the input rational expression that we got it, input problem. And if we check out the denominator, the checkpoint is, can it be factorized? And the answer is yes, because it can be factorized into this format, which is x minus 3 and x plus 1. And after doing the factorization, okay, that's the most important thing. If you see, that's the reason I put this in red. This is most important. After you're done with the factorization, and when you cannot factorize it anymore, you already come to the simple terms. You check out each of the factors. If each of the factor is linear in nature, meaning the degree of the x variable by itself over here is 1 and over here is 1. If the degree of each factor is 1 in terms of the x variable, it's linear in nature. And none of the factors are repeating. That is, they are non-repeating. For example, x minus 3 and x plus 1 are the two factors in the denominator, and both of them just appear once. They do not repeat. They just appear once. So what are the two conditions? It should be non-repeating. So once you factorize, the individual factors are non-repeating, and each of the factor is linear in nature. Okay, that's what this means. Non-repeating linear. It's non-repeating, and each of the factor is linear in nature, means the exponent or the power or the degree of the unknown variable x by itself is 1, linear in nature. After you factorize, okay, after you factorize, not before you factorize, because before you factorize, if you see, the degree is 2 and it's quadratic, but we are just doing the checkpoint, can it be factorized? And yes, it can be factorized. And after it factorized, the factors are non-repeating and they are linear in nature. Each one of them is linear in nature. In this case, this kind of polynomials are called as, they can be resolved by this kind of expressions are called as non-repeating linear factors, and they can be solved in a specific method while we solve it, the partial fraction in the next episode. That's the type 1. Okay. Similarly, if you see over here, the given expression appears quadratic, but if you just focus on the denominator, you can apply a square minus b square and you can expand it. And if you see, after factorization, we get 3 linear terms which each one has a degree of 1 or the power of 1 on the x value itself. The immediate power of x is 1, and each one is non-repeating. None of the factors are repeating. You have got this factor x, that's only appearing only once. We have x minus 1 coming up only once, and we have x plus 1 appearing once. So none of these factors are repeating, or they are non-repeating, and they are linear. So this kind of examples belong to this type 1 of partial fractions or proper partial fractions, which are categorized as non-repeating linear factors. Okay, let's jump to type 2. In type 2, it's exactly similar to type 1, but instead of non-repeating, it could be repeating in nature. So what is type 2 of proper partial fractions? They are repeating linear factors. Okay, and what does it mean? Let's take an example over here. Let's take this example. In this case, at the bottom, if you see, there is one linear factor and one quadratic. But as always, we need to check if any of these expressions can be factorized or broken down into simpler terms. The answer is yes, because this x squared minus 1 that we have seen several times is kind of fitting in the identity of a square minus b square, and it can be factorized as a plus b into a minus b, which is what we have done here. So this first factor remains as it is from here, but the second factor, which is quadratic in nature, we are factorizing into these two terms using this identity. Now you see here, now we have broken down this given rational expression. The denominator is broken down into three factors. Number one, that's the thing. All the factors are linear, meaning the power of x by itself is 1. So that's linear is there. But after factorizing the first two terms, this one, the x plus 1, the x plus 1 is repeating. It's repeating twice. It's one time and two times. So if you see here, I put this way, this is repeating. So although this is a linear factor, this is repeating, and hence these types belong to something called as repeating linear factors, where the degree of each factor is still 1. So don't get confused. The degree of each factor is still 1. Even over here, this exponent is still 1 over here. So it's linear in nature. But some factors are repeating, which in this case, this factor is repeating. It's coming twice. And again, all these things you should see after factorizing, not in the given equation. First, you should always see if you can factorize the equation. And once you factorize, then you have to see whether it's type 1 or type 2. Okay. One of the big things, let me just remove this. One of the big things that in the red color where people normally get confused, and I want to just take a minute to explain that, is confusing the degree with the power of the x. So over here, when we say degree of each factor is linear, we are talking about the immediate power of the x variable by itself. The x variable is here, power of here, power of this x, power of this x, power of this x, power of this x, and power of this x. For example, in this case, the power of x is still quadratic. It's not linear, it's quadratic. But since we can factorize into linear factors, the power of each of this x by itself is 1. Okay. So and since these two terms are repeating, let's say the given problem to you was like this. Okay. This was the problem. And over here, you can easily see that the first factor is repeating. Okay. But still, after you expand that into this format, it still gets broken down into two linear factor. X plus 1 the whole square is equal to x plus 1 and into x plus 1. So once you factorize it or simplify it, the degree of each of the x or power of each of the x is still 1. So do not get confused with this power, which is indicating that the factor is repeating. Do not get confused with this power with this power. Okay, these are two things. So you have to see what is the power of the x and not what is the power of the repeating factor, which is just means the repeating, which you can simplify, and I can always write it this way. So assume that you're not writing it this way and you're just focusing on this. In this case, it's clear that you have simplified it to the max, and then when you see the power of x by itself, it's 1, 1, 1. So just keep that in mind. That's the reason I put this in red. Do not get confused with the square factor, this factor, okay, and the degree, the power of variable x by itself. Okay, do not get confused. So we are not talking about the degree of the factor when it's repeated. We're talking about the power of x by itself. That's what we're talking about. So that's kind of an important caveat in pretty much both the types, the type 1 and type 2, so that you don't get confused. And again, first you have to always check whether you can factorize in both the types. Okay, if it's factorization possible, break it down to the simplest, spread it out completely, and then decide whether is it an example of non-repeating or is it example of repeating linear factor. That's type 2. And the last type in the context of proper partial fraction is where you have a quadratic in the denominator, and that cannot be factorized. If you see, both these expressions are quadratic in nature and it cannot be factorized, which we have seen. Whereas in both these cases, in type 1 and type 2, you still did have a quadratic coming down in the denominator. All these examples are still having quadratic, but those quadratic can be factorized into simpler linear factors, and hence it belongs to a different type. Whereas over here, this kind of expressions, quadratic expressions, you cannot factorize. You have to leave it as it is. If you remember in the previous video, the checkpoint 3, where we discussed sometimes factorization is not possible, quadratic expressions. In that case, we just leave it as it is. And these are the same two examples that I've taken. It cannot be factorized. So in such cases, which is type 3, you might get a quadratic and you cannot factorize. So you just leave it as it is. We'll solve it in a different way. And that's kind of the type 3. So those are the three types of problems within the context of proper partial fractions that we might get while a given problem is supposed to be decomposed into a partial fraction. That means we have a rational expression, which is a ratio of polynomials, and our objective is to decompose that into partial fractions in a simpler format. And based on which type it belongs, we'll have a different kind of a method to do that. And within quadratic, in some of the textbooks, they like how we are covered for linear. We are covered for linear as repeating and non-repeating. For quadratic also, in some textbook, they might call out quadratic repeating and quadratic non-repeating separately. Both these examples are non-repeating, but in some cases it could be repeating quadratic. For example, let's say the same example over here, if you had 3x minus 2, and at the bottom we had x square plus 4, and we have got repeating. So it's twice. In that case, it becomes an example of repeating quadratic. But since the methodology is not very different, I'm not counting that as a separate type. But if it comes, you can very well, if you understand this type, you can always solve. And that's why I put this in a kind of asterisk, saying that other varieties could include repeating quadratic factors, which are kind of included in this. If you understand this, you can solve. So summing up, three types of problems for partial fractions: type 1 non-repeating linear factors, type 2 repeating linear factors, and type 3 quadratic. And in the next 3 or 4 episodes, we will take each type and see how to solve and how to attack the problems based on the specific type of problems. More coming up in the next episodes.